All right, I thought I would quickly run through the last couple handouts, so you have all the handouts relevant for exam 3. And again, this is meant that I'm going very quickly, and then you are filling in the blanks with everything I'm not displaying. An ice skater with some mass and velocity is ice skating in a straight line towards a pole, which has its own mass and length, which is attached to a rotating pivot. The pole is stationary. The skater runs into the pole and holds tight, causing the rod and the person starts spinning around. Describe the resulting angular motion. The resulting angular motion, if they grab on, they and the rod will start to rotate counterclockwise. I could say in that case that omega points out of the page if I wanted to describe the overall angular velocity that results after this collision. Collision being key here, because with collisions we can typically use angular or linear momentum. All right, define the system as the rod and the person. Consider the times immediately before and after the collision. What quantities are conserved? So angular momentum in this case is a conserved quantity. Essentially, we're saying that our system is rod plus person, which allows us to look at all the interactions in between the rod and the person occur inside the system. And because of that, all the torques that occur are inside the system. There's no net external torque. Angular momentum is conserved. Write down the total amount of angular momentum right before and after the collision. So essentially you can think of this as a rod, which is not moving, and then you have a point particle that is moving towards the rod that has some mass little m. And this pivot is going to serve as our axis of rotation. Immediately before the mass hits the rod, it is essentially a length L away from the axis of rotation. So we can write the angular momentum initially as the magnitude of the moment arm cross the momentum the person has, which in this case is just the length of the moment arm times the momentum the person has multiplied by the sine of the angle between the moment arm and the person's momentum. But in this case, the moment arm, I guess R, which goes from the axis of rotation to the point of contact, and the direction of the momentum, which is straight up, is a 90-degree angle. Sine of 90 degrees is just 1. The initial angular momentum is just LmV. If I wanted to say this as a vector, I would say it's LmV and points out of the page. For L final, so I guess this is L total, the total linear momentum initially. And the total angular momentum initially, total angular momentum after the ice skater grabs on. Now the ice skater and the rod are moving as one big extended object. Essentially, it is a extended rod with mass big M and length capital L. And then there's a point particle of mass tagged onto the end. So for extended objects, you can always write this as I omega. If the entire object is rotating as one big unit, in which case it is. So in this case, it amounts to writing this as I rod plus I skater, and they are both rotating with some angular velocity omega. The skater is just, its rotational inertia is just ml squared. Because it is a point particle. Point particles are defined, their rotational inertia as their mass times the length between the axis of rotation and their location squared. The rod, we have to be careful because if we were to look up in our table, we would get that for a thin rod that has an axis of rotation here, the rotation is 1/12 ml squared. But in this case, that's not where this rod is rotating. The rod, in our case, is rotating here. not through the center. The entire rod is rotating around this dashed red line. So we have to use the parallel axis theorem. We can take the center of mass answer, and we can add onto it the mass of the rod plus the square of the shift, which in this case is L over 2 squared. I'm shifting, from the center of rod to the edge of the rod. That distance is L over 2. All of these give us numbers, except omega, which we do not know. And then the conservation law is that L little mv then equals I total omega. And essentially you know everything except omega, and you can solve for omega. Before the sun became the sun, it was a big puffy protostar. Its self-gravity caused it to contract to a smaller size. As a result, it spun up. This is essentially the celestial version of the ice skater pulling their arms in. If I define my system as the sun, it is contracting because of its own internal pulls of its own gravity is pulling on itself. And so as a result, all the forces are internal. As a result, angular momentum overall is conserved. So in this case, I can say L initial equals L final. Or since this is an extended object, I could write this as the initial angular momentum, I omega, is equal to the final angular momentum, I omega. I for a sphere is 2/5 mr squared. And essentially we're told that m final equals 1/100th of the radius initially. So I think I said m. R final is 1/100th of the initial radius. The mass is not changing. And we ultimately want to find omega final, which I'll note is the same thing as 2 pi divided by the final period. And the initial angular velocity is 2 pi divided by the initial period, which we do know. So I could also write this expression as just I initial over T initial equals I final over T final. There's some 2 pi's as well, but they're on both sides and would cancel out. So I might write this as T final over T initial equals I final over I initial. Which is kind of nice because I've conveniently set this up as a ratio. I final is then 2/5 m r final squared, and then the denominator is 2/5 m r initial squared. The 2/5 cancel, the m's cancel. This is just equal to r final minus or over r initial all squared. The initial radius was 100 times the final radius, so then this is 10 to the minus 2 all squared, or this is 10 to the minus 4. As a result, the rotational period of the sun is 10 to the minus 4, the initial rotational period, which if that was 100 days, this then becomes 0.01 days. The amount of time it takes to go through one orbit has significantly decreased, or its angular velocity has significantly increased. You could find the angular velocities and find that they would have increased by a factor of 10 to the 4. Suppose you're located at the center of these concentric circles. The outer circle is twice the radius of the inner circle, and each particle has the same mass. There's either 1, 2, or 4 particles at each location, or maybe 0. On the left, identify masses or combination masses that cancel each other out and mark them with an X. On the right diagram, draw an equivalent setup with the red dots, such that what is the overall net gravitational force felt by an object at the center. So this gets into the idea of superposition, where the fact that this guy is tugging, actually let me not do that as the first example. The fact that if this object is tugging the center towards the bottom right. This object is tugging the center towards the the bottom left, and then the one in the upper right is pulling towards the upper right. They are the same distance away from the center. By superposition, they cancel each other out. There's no net force from those two. Similarly, these cancel each other out. Similarly, these cancel each other out. And then one of these cancels out one of these. So then the net result is just this. So the net gravitational force is towards the lower right. Similarly, this cancels this, this cancels this, this cancels this. There's a net gravitational force to the left. Here are the easy ones, is this cancels this cancels this. And now what's going on here, this single particle on the right is pulling the object to the center to the right. And then each of these four particles are pulling the object to the left, but they are each individually exerting a weaker gravitational force on the object at the center. Right, since it's gmm over r squared or d squared, the particles that are twice as far away exerts 1/4 the force. The denominator doubles, but then you square it, so the overall force goes down by a factor of 4, or it's 1/4 as strong. So each of the particles on the left pulls with 1/4 the force as the particle on the right. But there are 4 of them on the left, so they all collectively cancel out the one on the right. And there's no net acceleration in this case. Similarly, this cancels out this. That's essentially what we just did. This cancels out this. And then one of these cancels out all of these. And so as a result, there's a net gravitational force towards the lower left. Earth orbits the sun once a year at a distance of 1 astronomical unit. It orbits the sun in a circular orbit. Come up with an expression for the velocity of the Earth around the sun. So in this case, you got the sun and the Earth going around in a circular orbit. So it's at some radius r away, always from the sun. Circular orbits suggest uniform circular motion. So Newton's laws say the sum of the forces equals the Earth's mass times its acceleration. The force in this case is g m sun m Earth over, let's call it d squared. And that equals the mass of the Earth times the Earth's acceleration. If this is uniform circular motion, this is just v squared over d. One of the d's cancel, the mass of the Earth cancels, and you're left with v squared equals g m sun over d, or that the velocity of the orbiting Earth is g m sun over d, all in the square root, which in this case is 30 kilometers per second. Is this velocity smaller or larger for Jupiter? What about Venus? So notice this expression only depends on the mass of the sun and the distance of the planet. So the numerator does not change, but as you get farther away from the sun, d increases, this entire thing gets smaller. Jupiter orbits slower. Venus, therefore, being closer to the sun, orbits faster. And the general trend is the farther away you are from the sun, the slower you move. Which is kind of like Kepler's third law, where the period squared goes as the semi-major axis cubed. Right, not only do you have more distance to cover the farther away you are, but you're also traversing through that distance slower. What is the angular velocity of the Earth? So you could take, remembering that for circular motion, that's at some radius d, and is moving some velocity v perpendicular to that circle. The angular velocity times d is equal to v, so I could find the angular velocity as v over d. I think the alternative mean is that I could also remember the angular velocity is 2 pi divided by the period. So I could also, knowing that the period is 1 year, figured it out that way too. Surface gravity on the surface of an object is given by g, the mass of the object, divided by the radius of the object squared. When you plug in the values for the Earth, this becomes 9.8 meters per second squared. And the idea is to look at this for different planets, and essentially it's asking for some sort of ratio. So I'll just do Venus. So if we look at this table, it's giving you the ratio of Venus's mass and radius to the Earth's mass and radius. That's what the units are written in. So it says that the radius of Venus is 0.95 the radius of Earth. So if we go back, I could write that R Venus equals 0.95 radius Earth. Then if I look at the mass, it looks like it's 0.815. So then M Venus equals 0.815 the mass of the Earth. And the idea is I can figure this out by a ratio. If I want to know what fraction g of Venus is compared to 9.8, or g of the Earth, then algebraically I can just plug in symbolically I can just write this as the ratio of two different equations. It's kind of nice that the g's cancel. And then this becomes mass of Venus divided by mass of the Earth. And then this becomes the radius of the Earth divided by the radius of Venus, all squared. And the fact is that I know what these ratios are. Looking at what's on the left, I know that this is 0.815. And I know this is 1 over 0.95. But I can't forget that squared. And so if I square that, then I will get, it will be some small number. So then that says, let's call it, eta. So then it says GV is whatever that number is times 9.8 meters per second squared. Fine, let's plug in G. I am not going to, but I will set this up. This is an example of Kepler's third law. Each of these are slightly different. But the idea is that there's a relationship between how long it takes an object to orbit around a central object, its semi-major axis, or the distance between the object, the center object, and the orbiting object, and the mass of the central object. The idea being that this is the central object. The sun, if it's the Earth going around the sun. Jupiter, if it's the moons of Jupiter going around Jupiter. And the idea with all of these is I give you either P, R, I give you two of either P, R, M, and you can solve for M. I guess we're focusing on the mass. So I guess in all of these cases, I give you some way of determining P and R. Here I just give you R, and then here I just give you P. Just got to be careful about the units. Let's see, moon orbiting the Earth. This many kilometers are traveled every 227.3 days. So here I essentially gave you the circumference, 2 pi r. And then this is giving me the period P, etc., etc. I don't think anyone got to this, but Jupiter is the largest planet in the solar system. The most of the mass resides in the sun. The sun is blah, the center mass of the solar system, inside or outside the sun. So essentially, you can imagine if you take the sun and then you have Jupiter, and I'll put the sun at the origin, and then Jupiter is all the way out here at about 5 AU. You can look that up on the table. You could essentially say that the center of mass of the sun plus Jupiter would be M sun times the location of the sun, which is 0, plus M Jupiter times the location of Jupiter, all divided by M sun plus M Jupiter, the total mass. If I put the sun at the origin, this is 0. You could plug in numbers, and for just Jupiter and the sun, you should find the center of mass is still inside the sun. And I think if all the planets happen to be aligned, you can pull the center of mass outside the sun, but I don't think that ever happens. Right, so the idea is that Jupiter then is orbiting the center of mass. The sun technically is also orbiting its center of mass, though it appears like the sun is just wobbling around. It obviously takes the same amount of time to complete this orbit. All right, oscillations. Escape velocity is the velocity needed to escape to infinity. You throw a ball off the surface of the Earth with some initial velocity. What is the total energy initially? So here, I say it's 1/2 mv squared minus g m Earth little m over r, where r is the radius of the Earth plus the height you're off the surface of the Earth. I guess from the Earth's surface. So I guess you're starting essentially with h equals 0. Again, remember that you measure things from center to center in terms of for spherical objects. Also notice that I used minus gmm over r and not, say, little mgh. The reason for that is I know I'm going to be considering my final position, right, where I'm all the way out at infinity, which is going to be much, much farther away from the Earth. Little mgh, to say that the potential energy is little mgh only is true if the gravitational force is given by little mg, or that 9.8 meters per second squared is a relevant gravitational acceleration, which is not true once you get, a couple hundred kilometers off the surface of the Earth, let alone escape to infinity. So in that case, it's more useful in this case to use the more general version of gravitational potential energy. You, of course, could do, if you always stayed near the center of the Earth, you could, of course, use either and get the same answer just as well. If you were able to barely escape to infinity, that's essentially saying you get farther and farther away, get slower and slower and slower, finally get to infinity, where your kinetic energy has essentially gone to 0, and your potential energy, g big M little m over infinity, is also essentially 0. The total energy then is 0. At infinity. Then it asks for the escape velocity, so it's 1/2 mv squared minus g big M little m over essentially the surface of the Earth equals 0 by energy conservation. Gravity is a conservative force. I can, of course, use energy conservation. You can solve this to get 2g mass of the Earth over radius of the Earth is the escape velocity. If you started right at the surface of the Earth, that's how fast you need to be going to make sure the Earth doesn't eventually pull you back. What distance should you launch the ball? So then it does a bunch of ratio problems using this. So I'll just do one of them. I'll do number 2. What mass of the Earth would increase the escape velocity of an object launched from the surface to be 3 times as large? So again, essentially I have 2 things I'm comparing, a new scenario and an old scenario. This is saying that the new scenario has an escape velocity that is 3 times the old scenario. Nothing is being mentioned about the radius of the Earth changing, so it stays the same. And then the question is, what mass is needed to achieve this? And again, I could start just by plugging in the equations themselves, not worrying about numbers, not worrying about relationships between these variables. In this case, the 2's and the g's cancel. And looks like I'm left with the new mass divided by the old mass to the 1/2 power. And then since I have a fraction of fractions, this becomes the old radius to the new radius to the 1/2 power. The radii are said to be the same, so this ratio is just 1. So that's simple. This ratio is 3. That's replaced with just 3. again, based on what we've written here. So then this says 3 equals the square root of new mass over old mass. Again, can't forget the fact there's a square root, or 9 is the new over the old, or the new is 9 times the old. So again, the setup is always the same for ratios, right? What is your relationship between the two scenarios? Essentially, find the equation that connects all of those variables and just divide it by itself with plugging in different variables for the numerator versus the denominator. Simplify, it will essentially turn into just a set of ratios, and then plug that in order to then get to your final answer. The optional is essentially if you set the escape speed to the speed of light, you can then solve for the radius, which is then 2gm over c squared, which is the Schwarzschild radius, or the radius of the black hole that has some mass m. Since the speed of light is enormous, this radius tends to be quite small for things like, I think for the sun, it's 2 kilometers. You would have to cram the entire sun into a ball that's only 2 kilometers wide for it to turn to a black hole. All right, you have an electric shaver whose razor blade moves back and forth over a total distance of 2 millimeters. So essentially, if we were to plot the position of the blade as a function of time, it might look something like this. And it's saying this entire distance from top to bottom is 2 millimeters. So therefore, its amplitude is half that, or 1 millimeter. Amplitude is from middle to top or from middle to bottom. What is the angular frequency of this motion? We're told the frequency is 120 hertz. We know that the frequency is 1 over the period, which implies the period is 1 over the frequency. That actually gets us the third one. We're also told that the period is 2 pi divided by omega. So I could combine, say, these two and get that omega is 2 pi divided by the frequency and get a number there. Essentially, this is the relationship between all 3 of these variables. If you know one of them, you know all 3. They are not independent. What is the mathematical expression? So in this case, it might be x equals the amplitude cosine of omega t, where we just got a number up above for omega and we got a number for the amplitude. V, therefore, is a omega sine of omega t, employing the chain rule. This gives us the velocity as a function of time, which will oscillate up and down. If I were to plot this, it might look something like this, as time goes forward. So clearly there is a point where it's maximized, or has the largest, amplitude or magnitude. I just gave it away. That maximum magnitude is the amplitude, which is whatever is in front of the trig function, ignoring negative signs and whatnot. So then I would say V max in this case is just a omega, whatever that is. Similarly, A is negative a omega squared, and then we're back to cosine of omega t. Again, I could plot that. That would look something like this. Clearly, there are points where the acceleration appears maximized, which again is just whatever the value of a omega squared is. You always have to be careful with units. In this case, capital A has units of meters. Omega has units of radians per second, but degrees are one of those units where you don't really need to ever, you can ignore the fact they exist. So omega you can write this as 1 over seconds. Angles have no physical meaning really, which is why they're kind of an optional unit for these sorts of things. So in this case, this is indeed meters per second squared, for example. All right, number 6 was quite hard, so I think I'll only do number 5. Consider a bullet of clay that's shot into a box. the box is initially at rest, the clay hits and sticks to the box, at which point the entire system undergoes simple harmonic motion. What is the final velocity of box clay after the collision? So in this case, I'm looking at a system immediately before the collision and immediately after the collision. There is a very strong interaction between the blob of clay and the mass of the box, so I can utilize momentum conservation as a result. The initial momentum is little mv, and that is equal to little m plus big M, which all get together, times the final velocity of box plus clay. So this is an inelastic collision. And it's whatever this evaluates to be, where this is that. Now it has some motion, so now it's moving to the right. The spring is going to get compressed as a result, and then it's going to try to push the box back to the left. And as a result, the box is going to undergo simple harmonic motion. By considering a free body diagram, what angular frequency would you expect? So in this case, the box is moving to the right. The spring is getting compressed and is going to resist that. So the spring is going to push back out with some force, kx, where x is the amount of compression. By Newton's second law, the mass times the well, I should be careful. The mass of the clay plus box times its resulting acceleration equals negative k the x. If the positive direction is to the right, then the spring is pushing the box to the left in this case. In this case, I can say that the acceleration is minus k over the sum of the masses times x. It is of the form negative a number times position. It therefore is undergoing simple harmonic motion, where this quantity here plays the role of omega squared. So I could write that omega is the square root of k divided by little m plus big M. And I can get some number. Using your value for omega and by considering the functional form for the velocity, what is the amplitude of motion? So the idea here is the velocity it was something like negative a omega, was it cosine? No, because the negative sign popped out, so it was sine of omega t plus some phase angle. You could figure out what the phase angle is. Turns out in this case it's going to be something like 90 degrees. That will turn the sine function back into a cosine function. Or you could just think what's happening. The box starts here, moves to the right. The spring then pushes it back. It will overshoot, and then essentially will oscillate back and forth around its initial unstretched equilibrium position. Very similar to what we looked at when we went the vertical box on the spring for the quiz. So it is starting at the equilibrium point where the spring exerts no force, which is also where the velocity is maximized. So that velocity that it has that you solved for, v final, is the maximum velocity the box will have, because as it moves to the right, it will only slow down in velocity until it comes to rest. And then it will start to gain velocity as it moves back to the left. It will overshoot the equilibrium position, at which point the spring will start to be stretched out and will start pulling the box back to the right. So you could just say that a omega equals v final, taking what we got before. You know omega, you know v final, you could solve for the amplitude and figure out how much it moves. You could also have done this by work energy, just by considering how much the spring compresses before it takes away all the kinetic energy. You will, of course, get the same answer. All right. Oscillations of not a simple kind of pendulum that's undergoing a small angle displacement and is undergoing simple harmonic motion. And the first step is to prove that's the case. What relationship between the angular acceleration and angular position must be obeyed? A lot of people said something like this, which is true for linear motion. So then the angular version is something like this. If I can show the angular acceleration is negative a number times theta, that is uniform circular not uniform circular motion, that's simple harmonic motion, for this pendulum that is oscillating, around the vertical position. What is the rotational inertia of the pendulum? Treat the bob as a sphere. So in this case, you have a rod and then a bob. I rod is 0 because it's assumed massless. Then I sphere, you might think is just 2 pi, the mass of the sphere, the radius of the sphere. But remember, inertia depends on your axis of rotation. And in this case, the pendulum is oscillating about this axis of rotation. Not a line that goes through the center of the sphere, rather a line that goes somewhere along the roof, kind of parallel to the roof. So we have to shift this over by some distance h, which in this case, based on the drawing above, is just the length of the rod L. So then by the parallel axis theorem, it's not just 2/5 mr squared, but plus ml squared. You're shifting it by a length L. So the rotational inertia for the sphere is whatever this quantity is. What is the total torque on the pendulum? And you have some moment arm reaching out to the bob. There's a gravitational force that is pulling downward from the center of mass of the object. The moment arm. The torque, as a result, is the moment arm cross the force due to gravity, which is just the length of the moment arm L, mg, times the sine of the angle between them. I would also throw in a negative sign, because the tendency here is that the object is going to want to rotate clockwise. And I say up above that you can approximate this as L mg theta when sine is small. When thetas are small, then that is the case, which is key for this next step. What does Newton's second law say? So the rotational version of Newton's second law is that the sum of the torques equals I alpha. In this case, there's one torque, so it's L mg theta equals I bob or sphere times alpha. Or I can say that alpha is minus L mg divided by I times theta. In this case, I have again shown alpha can be written as minus some number times theta. Whatever this evaluates to plays the role of omega squared. So omega then is just L mg divided by I sphere, which again, remember that utilizes this entire thing for the rotational inertia. And that's some number. I could have turned it into a period as well, got that number, and then also calculated was the period of this oscillator by 2 pi over omega. Theta does not appear anywhere here. The only place it appeared, really, if at all, is the assumption that the initial angle was small, so that the theta values never got very big, which allowed us to always say that sine of theta was equal to theta. This one is tricky. If theta is blah, what is the maximum linear speed of the bob? So in this case, you have enough information where you can write down the right? The oscillator might look something like this, right? If I call this theta naught, or the natural frequency. Unfortunately, we just don't have it. The symbols get reused here. So then the angular velocity, unfortunately also given by omega, is then negative this natural frequency theta naught times sine of omega naught t. You might think that then the maximum speed of the bob is just this, and you would be almost all the way there. But if you look at the units of this thing, it has units of radians per second. So it does not quite have linear units. But then, of course, remember, if you have something that's undergoing circular motion and it's a distance r away, then omega r equals the velocity in that case. So the idea is that you could take omega naught, theta naught, multiply it by the length of the pendulum, and that gives you a Vmax in this case. Yet another ratio problem. If I double the length of the pendulum, how does the new period compare to the original period? First things first, you should be able to at least argue to yourself whether it should increase or decrease. You're making L bigger. L is in the numerator, therefore I would expect the period to increase as well. Now let's see that. In this case, L new equals 2L old, G new equals G old, and T new equals something T old. I could start by the ratio of this equation. The 2 pi's cancel. You just get this kind of ratio of the square roots. But the g's are the same as well, but I'll simplify it anyway. So this is ln over L old, and then the square root of G old over G new. Again, rate fraction of fractions, so you got to be careful. This goes away to unity because they're the same. This is twice L old over L old. Those cancel. This just becomes the square root of 2. As a result, T new equals the square root of 2 T old. No. Suppose I have a string that is held taut. I shake the string so that a traveling wave is described by this. Given this information, what are a bunch of things? So remember, for a traveling wave, you can write this as some amplitude sine wave number times position minus angular frequency times time. So essentially you can connect the amplitude in this case is 0.00327 meters. The period of the wave, the period is given by 2 pi omega. But we can read off omega in this case is 2.72. So then you can plug that in, I guess, per second, or radians per second. The wavelength of the wave, so this is the new things with traveling waves. The wavelength of the wave is saying how far do you have to go in distance before you start to see things repeating. The period tells you how, if you look at one particular point on the string, or whatever is oscillating, when do you see that point start to repeat? The wavelength says, where do I go in position to find repetition? That is related similarly to this thing we call the wave number, which is the number that's in front of x. So in this case, the wave number is 72.1, I guess, radians per meter. So you could plug that in. The wave speed, I derived in lecture to just be omega over k. You can show yourself that you can also write it as lambda times the regular frequency if you wanted to. But in this case, we know omega, we know k. Or you can also write this as lambda over the period if you want, if that's easier too. So you know enough on the right-hand side that you can figure out the velocity. A rope with mass density mu is held steady with tension force T. Based on dimensional analysis, how will the speed of the wave scale with these variables? I did this one in lecture. You can show that T over mu, all in the square root, is the only way you can get it so that the units make sense, so that the units on the right-hand side have units of meters per second. There's no other way you can combine these two variables to do that. So what this says is that the velocity, whatever the answer is, no matter how complicated the math, it must be proportional to the square root of T divided by mu. But it turns out, in this particular case, when you do all the crazy math, it just ends up being unity. You shake the string with a frequency f, the waves travel thus down the slinky at or rope with a certain speed v. You then triple the tension in the string. How does the speed of the wave change as a result? So in this case, you could say v new over v old. And utilizing the fact that you know that the velocity of waves traveling down the spring or the string or the oscillator or whatever, traveling waves move through a medium and only their velocity only depends on the medium itself. You know, the temperature of the air for sound, the tension in the rope in this case for a slinky or a rope wave. You know, it depends on the medium they're traveling through. So in this case, you might say the tension has tripled, the mass density has stayed the same. This just becomes the square root of 3. So the speed of the wave increases by a factor of square root of 3. How does the wavelength of the waves change as a result? You are shaking the object with the same frequency f. That has not changed. You have not changed how much you're shaking the string. But the velocity has increased by a factor of square root of 3. So then I'll let you do the ratio, and you can show them that the new wavelength is also square root of 3 times longer as a result. All right, light moves incredibly fast. Sound moves relatively much slower than light. The question is the difference in when you see lightning and thunder divided by 5 approximately the number of miles the object is away? So the object is 32.2 kilometers away, or 32200 meters. This essentially is a chapter 2 problem where distance equals velocity times time, or in this case, delta t is the distance traveled divided by the speed. In this case, you would plug in the speed of light and get something that's incredibly small. In this case, you'd use the same d but plug in the speed of sound and get something that's like 90 seconds. And then that change in time, this is essentially 0. You essentially see it instantaneously. I think this ended up being something like 90 seconds or so. 92 point something or whatnot. So the difference in times is about 90 seconds, and when you divide by 5, you get something that's 18 point something, 19, something that's close to 20, which was the claim. That it's if you divide the difference by 5, you get a number. The units are obviously nonsense, but you get a number that essentially is close to the number of miles. You could try to convince yourself why 5. Essentially, it just depends on unit conversions between meters per seconds, miles, and etc. And then this was just kind of a comment on what I just said. The delta t, the difference in the two times, is essentially the distance divided by the speed of sound minus the distance divided by the speed of light, which is the same thing as the distance divided by the speed of light, speed of sound, multiplied by the speed of light minus the speed of sound. But this thing in parentheses is essentially just the speed of light, given how much faster the speed of light is. So then this just simplifies to d divided by the speed of sound. The speed of light cancels in the numerator and denominator. Again, since you essentially see it instantaneously, the only thing the lightning is doing is telling you when to start counting or when to start your stopwatch. and then you're just essentially waiting for the sound to make it to you. Alrighty.